All right, I think we have enough people to get started. All right, everyone, welcome to lecture 31 for GPU mode. So very much like it's sort of in line with the rebrand. I'm really glad we have like Nikita Shulga, who goes by Malfit on GitHub here to give us a beginner's guide to writing metal kernels. So I first met Nikita like just about like when I joined PyTorch. I think to this day he's still like the second biggest contributor to PyTorch with like 2,000 plus commits or so. So it's like someone like highly productive that I really admire at work. And I've personally learned a lot like looking over his shoulder, like while he's coding. So I'm hoping we can have sort of something very much in that vibe. So yeah, without further ado, Nikita, please go ahead and get started.
Thank you for the introduction, Mark. So first of all, the disclaimer. So this is a beginner guides to metal kernels. It's not because like I'm an advanced engineer and want to give you some basics. I also don't know what I'm talking about. I'm just writing code, right? So beginner's guide to metal kernels is sort of a little bit of a summary of my own learnings of GPU programming and learning how to program in metal. So let's begin. Oops, sorry. So preamble, why we're talking about this. Laptop the slides are streamed from is a pretty powerful machine, but if you compare the CPU performance to GPU performance, again, I did a napkin math, I didn't measure it, but like this one have 8 cores running at 3.5 gigahertz. So that gives us about, and it can execute 4 floating point operations per second. So that gives us about 110 gigaflops. On the other hand, this machine have like a 19-core GPU, which again, like if you do a napkin math, that gives you roughly 7 teraflops of GPU performance. I don't know if it's possible to achieve this theoretical throughput. I haven't been able to, but at least that's the theory. A lot of those GPUs are not CUDA capable because they're manufactured by Apple and they have a very different architectures than CUDA kernels, and also CUDA is very specific to NVIDIA. So we couldn't use it right away with any ML applications. Again, a little bit of a history. So MPS backend was first released in PyTorch 1.12 to expose more hardware features. Unfortunately, it doesn't cover all the operators that one might need to run the kernels, especially in the early stages. We run into lots of situations when we wish something was working, but it wasn't. And also, on the other hand, MPS, which stands for Metal Performance Shaders, interoperate nicely with metal. So MPS is actually nothing more than metal. Well, some professionally written metal kernels, so like the ones you're going to see today. So it must be fun to learn to code some. And again, like if you know CUDA, you probably already know 75% of metals because all GPU languages are alike. Let's go with a little bit more history. So how all this like GPU programming started, because it feels like, you have a gaming PC and you want to see graphics. Why do you want to do machine learning on it as well? So OpenGL was released in 90, by the way, all the illustrations here, except for the screenshots, was generated by ChatGPT. So the typography is as amazing as it is. So in 92, OpenGL 1.0 was released to accelerate graphics rendering, but unfortunately had only fixed pipelines. What does it mean? It means that if you want to render something, you need to submit number of triangles, say how those triangles bind textures, and specify where your light sources are. And you can have up to 3 light sources if you have like a consumer GPU, and I think in 95 you can have up to 16 for a professional ones. But you cannot do much without it. And people realized very quickly that they want to have shadows, they want to have transparency, and you can't really do it with fixed pipeline. So around OpenGL 1.4, something called ARB, which is application, I keep forgetting, but essentially it's an OpenGL extension, was introduced something called GSLang. Before that, it was ARB ASM. And finally, in 2004, something called OpenGL 2.0 was released that have a programmable shader. Still, we pretty far away from ML programming. It's just a generic graphics shaders. They have 3 precisions mode, low, medium, and high. But I don't think any one of them was actually FP32 precision. Well, maybe. Around the same time, people noticed that using something called fragment shader, you can accelerate scientific computations by a lot. So some of the GPUs have a proper FP32 in the high precision mode. Optimization, and Ian Buck, who is one of the authors of the CUDA language, wrote a thesis about that when he measured how he can accelerate some, I forget the theme, but it wasn't like anything about ML, it was computational physics. So in 2007, I think CUDA 11.0 was released. And OpenCL, which was originally authored by Apple, but right now owned by Kronos Group, was published 2 years later, so around 2009, where I think CUDA 3 was Rage. And in 2014, 2015, like Metal replaced OpenGL and OpenCL across like languages or across all Apple surfaces. Why didn't people want to continue writing Metal? Because OpenGL was written back in 1990s, where CPUs was really not multi-threaded and not even a multi-core. So all the OpenGL pipeline was like a single pipeline that executes all the commands. And in modern both ML and gaming applications, you want to have multiple streams communicating with your graphic pipeline and executing some sort of operations. Anyway, so we're done with the history, and let's go a little bit into prerequisites. So because we're talking about Apple ecosystem, unfortunately or fortunately, in order to be able to write Metal shaders for any of the Apple devices, you need a Mac OS with the developer tools installed. And another thing is to interface. By the way, if you have any questions, I don't know, it's a bit hard for me to keep an eye on the Slack on the Discord at the same time. But if Mark, you have any questions posted anywhere, feel free to interrupt. Yes. Oh, thank you for the correction. So yes, it was public in 2007, was created, 5 to 6. But yeah, the thesis was published in, I think, 2007. But yeah, like all the work was done before that. Thank you for the correction. Oh, you can't unmute. I didn't mute you, Mark, so I don't know how to do anything. Okay, thank you. So anyway, because we're talking about Apple ecosystem, one have to be a little bit familiar with Objective-C or Swift to be able to dispatch this Metal shader execution. Sorry? Go ahead.
Sorry.
And you need to be able to write Metal shader language, or like read Metal shader language and eventually write to like dispatch something to GPUs. So the screenshot kind of shows the left part, how old school Objective-C looks like. I don't want to go into Swift because if most of the people familiar with C++ syntax, Swift is a little bit further away than Objective-C. So let's stick to Objective-C. And on the right, you see how Metal shaders looks like. They are very much like both of those languages are kind of look very similar to, I would say, C++. In particular, Metal shader language says that it's compliant with C++ 14 spec, but not the C++ 14 standard library. A little bit of a terminology, because I think I kind of do a little bit of a like alphabet soup. So Metal shader is a thing that runs on GPU. It is very similar to CUDA kernel. Well, I think in that case, it should be Metal kernel to CUDA kernel. So Metal buffer is just GPU memory. Interesting aspect of the Apple ecosystem is that in majority of the devices that was released recently, since GPU and CPU are on the same die, they share the same memory, and it can be shared without almost any performance penalties, which creates a lot of interesting applications. We can talk a little bit more about it later. So common buffer is more or less the same as CUDA stream. Sorry, I typed as I thought I'm typing, but I typed something different. Metal performance shader is a collection of optimized popular shaders that was written by people who know what they're doing, like me. So Apple released Metal performance shaders framework, and you can call them again using Objective-C or Swift to execute a highly optimized operations on the GPU. And finally, Metal performance shaders graph, aka MPS graph, is a graph-like compiler where you can fuse, well, it can fuse multiple operations under the hood if it chooses to. It might not. And this is a default interface that PyTorch uses to access GPU. Maybe interesting thing to mention that Metal performance shaders, even though it says it only runs on Metal performance shader graph library, even though it says it runs on GPU, it can also sometimes dispatch to Apple Neural Engine. but like there are no documentation when it does so, but you can observe sometimes that A&E is utilized. Now I think a little bit kind of away from long preambles and into how to do something practical for PyTorch. So if you want to write a metal shader as a PyTorch extension or just a regular 8 kernel, please use metal shader library class, which is defined in the MPS operation utilities to JIT compile your kernel source. And then kernel invocation from 8 looks as something that I screenshotted below, right? So this is from the cross kernel. I will go and post, we will have an opportunity to read code later. So I will probably like go through the slides and then it will become much more interactive. Okay, let me read. So, but how does unified memory model in CUDA compare to the unified memory model in Metal with M-series chips? That's a very interesting question. Again, I'm not an expert, so it is my own observations. It's not like authoritative answers that it's always like that. So first of all, like both CUDA and Metal are different. So if you're looking about like Tegra devices, so what is it? NVIDIA's Orin, where you have an ARM chip with GPU, it is very similar to Apple Silicon when memory is actually physically shared, right? On GPUs, it's very different. Well, like on traditional GPUs, when you have like x86 CPU and then you have your GPU sitting on the PCIe bus, like your GPU device is a bus master, so there is no really way to share the CPU memory to GPU other than say that like GPU can read CPU memory just like you, because it's a bus master device, it can make a request to the memory bus and read the memory. And similarly, GPU can map part of its own memory onto the CPU and CPU can read it. So I think those there is something called host pinned memory. So this is indeed that when you allocate something on the GPU and you can see this memory from the CPU, but you will pay performance penalty every time you do so. And also don't forget that GPU caches, even in case of the Apple Silicon, GPU caches and CPU caches are not synchronized. So if you want to see some GPU memory from CPU, make sure to clean your caches if GPU, like after you read it, because if GPU modifies the memory, you will be hitting the same like memory cache rather than actually reading from a memory. But like going back to the host pinned memory, so the benefit of having of GPU having a dedicated memory is that when you run in the kernel, you like guaranteed that no one else is accessing this memory. So GPU have a full memory throughput. With the system like Apple Silicon or NVIDIA Tegra, or I guess, again, I haven't seen them like this Grace Hopper devices, is that memory bandwidth is shared between CPU and GPU. So if your CPU is utilizing the memory, your GPU have a less bandwidth because it's accessing the same memory. So it will be slower. And the Kaustub asked the question about specific scenarios when MPS gets scheduled. I don't think it's ever documented when it gets scheduled, but yes, as somebody pointed out, you can say that you never want to schedule it on ANEs, and sometimes it might be scheduled, but again, nothing is guaranteed, right? So you hope it will get scheduled, but API is written in a way that you indicate your intentions that you want it to run on ANE if possible, but runtime, like whatever it is there, like not metal runtime. So if you write a metal shader, it will always be executed on GPU. But shader graph can choose to call ANE if matrix shapes, tensor shapes or operation types are sufficient, or if you're running in the correct like power mode. So sometimes it might say, well, it makes no sense to run on ANE because, well, ANE is not always faster. It's much more memory efficient. Andre have interesting observation. So yes, like why we want to write metal shaders even if your kernels are memory bound. So I don't know if people are familiar. So if for any applications, because systems like both CPUs and GPUs now on balanced systems, so they have more performance than memory bandwidth and other way around. So you want to perform more operations on the registers, which also called local memory on GPUs. Like GPUs have higher memory throughput than CPUs. So even if you're like memory bound, it's still beneficial to run your applications on GPUs because they will have like, well, depending on the particular M chip. So I think that's the difference between like basic, pro, and ultra, is that basic have like in basic machines, CPU memory throughput and GPU memory throughput is the same. On pro, I think GPUs have 2x more. And on ultras, maybe 4, maybe 3. I don't know the exact specs, and I guess it changes from generation to generation. But please don't quote me on that. Like, I read it at some point. I can't guarantee that this is exactly the numbers. But yes, this is the reason why, like, even though they share memory, GPUs have more memory controllers, so like more lines to access memories than CPUs. Cool. Let's go to the next topic. So how to profile debug metal kernels. Unfortunately, or fortunately again, on Mac, there are no better tools than Xcode. And that's the only tool that you have. To capture the kernel behavior, you can use MTL capture enabled environment variable, which allows GPU in a capture mode, which switches GPU in the capture mode, and then you need to decorate your kernel invocations with like a special instructions, and then you can open GPU trace and see what's going on. The same GPU trace can be used to debug kernel. I will demonstrate it later, or if people want to switch, we can do it now. But you know, if you really want to profile your metal kernel, what can you do? Well, unfortunately, you cannot. So there's no public APIs right now that allow you to collect any real metrics about what's going on the GPU, on metal GPU. But you can measure CPU wall clock time to estimate your kernel performance. So obviously it only, well, you better do it while running a large kernel, so you will know, because some of the time that you will be collecting is the time it takes to dispatch workflow to the GPU and wait for the GPU to finish the workflow. And make sure to sync your pipeline at the end. Otherwise, you'll be just measuring the time it takes to dispatch something to the GPU. So for example, see the benchmark unary example, which uses standard Torch utils benchmark timer primitives to benchmark GPU, like MPS execution time. And I've wrote this example so it can both be utilized on CPUs, on CUDA, or on Metal or MPS. Right, but it's important to put a synchronization comment at the end. Again, I don't know, like, do people want me to continue with the slide and then go into interactive examples, or should I go and like kind of show how it runs or whatever? Okay, let me continue with the slides. Unless, Mark, do you have a preference?
I think whatever feels right to you. Like,
okay, let's continue with the slides and then we kind of jump into the examples. So how to debug metal from command line? Again, it's not really a good idea, but you can use some sort of an environment variables, which is documented on, which are much better documented on a man page called metal validation if you're on your like Apple laptop, but the same environment variables are mentioned on the Apple documentation website. And you can see I made like an obvious mistake when I have an out of bound write in my kernel. If I do it without validation, it will just succeed. But if I define metal shader validation equals to 1 and then say want to see the report to standard error, it will print this message that execution function have an invalid write, which again, not ideal, but at least you know you're doing something wrong. And it kind of highlights a line number, which is also kind of a useful thing to have. So I don't know, like now I'm going to do with a case study. So one is accelerating GEMV. So GEMV is matrix vector multiplication operation. Why it's interesting to accelerate it? Because it's very important for LLMs. When you feed the token and want to predict next token, it's mostly GEMV operations. I think 70% of all the compute time is spent on GEMV. And a little bit of an interlude, or intermission or whatever, like, is AI ready to replace software engineers? I did it a few months back when Llama 2 was released, and I asked it the question to write me a fast matrix vector multiplication kernel using Metal. So first of all, it ignored my request about Metal and just wrote an OpenCL kernel, which almost the same thing. We talk a little bit about the distinctions, but this is what it wrote. To anyone who can read the code, it's not going to be performant.
So actually, I have a fun story. Do you know what OpenCL stands for? What the CL stands for?
Compute language?
That's not right, actually. It stands for Open Chris Latner. So yeah. Anyway, I'll let you get back to serious stuff.
I didn't know that. Is it true? Or is it a meme?
No, it's true. Like he told me this. So like it blew my mind when he brought it up because I think it's one of people seem to recognize him by LLVM, MLIR, and Swift, but like he was also one of the authors for OpenCL. So I think that's why he picked the CL name.
Interesting. Cool. I didn't know that. Thank you for the anecdote. So yeah, it's a very naive implementation. And so we will have probably 2 or 3 years of writing Metal kernels before AI catches up and replaces us all. So the very first thing that like AI did not pick up is if you want to do a better matrix vector multiplication, you should use, even though like GPUs are already massively parallel, you should still use single instruction, multiple data paradigm. So on GPUs, like whether it's CUDA, whether it's Apple Silicon, even if you write in all OpenGL shaders, there's always this like float 2, float 3, float 4 types, which again originate from the graphical nature of those pipelines, because when you do graphic computation, it's very important to have 4-dimensional vectors and 4-dimensional matrices. If you want to read about quaternions and graphics, that's a very exciting stuff. But let's not talk about that. So a very easy way to accelerate your performance by 2x or 3x is if you have a dense data, use float 4, and then you can perform the same compilation. It's the same computation is kind of a one operation, right? And also, again, because we are in the like graphic pipeline world, the very easy way to reduce 2 float 4 vectors is to do a dot operation, right? It does a multiplication and sum. So like code on the left is equivalent to code on the right, but the loop size is 4 times smaller and it runs 2 to 3 times faster. Second one is like to use another vectorized type called matrix 4x4, which is like, again, if you're using quaternions, matrices are very important, and the GPUs usually have a specialized silicon to perform matrix computations. So again, on our left, we see like a very simple vectorized kernel, right? When we use I missed the part that they are float 4s, but we're reducing float 4s. But if we multiply float 4x4 on the float 4 tensor, again, it's an operation that can be performed as a single operation, and it gives us the same results much faster. And the third step is to optimize memory access patterns. Go ahead.
So sorry, Nikita, this float 4x4, like, is it just that like Metal supports like variadic types? Like, is it sort of like arbitrary X by Y, or is this just like 4x4 because it seems like it's a tensor core like abstraction here?
So OpenGL supports, well, so 4 is maximum. I know there are 3x4 matrices because, again, sometimes you don't care about quaternions. You just want to rotate your triangles. And there are 3x3 matrices, right? I know that there are 2x2 probably, but I don't know if there is like, if it's fair to say that like your GPU throughput, if you do float 2x2 computation, will be what is that, 4 times more than 4x4 computation. I'm not sure. So probably like float 2x, like all of them are mapped to the same like 4x4 registers, and they just discard the results. So that's something I don't know. But the language itself allows one to have like float 3x4, float 2x2. I'm not sure if you can have like 1x4, or is it like always float 4 and then you need to transpose.
Interesting. Okay, thank you.
Oh,
Well,
okay. So yeah, 2, 3, 4, and half 2, 3, 4. Yes, and also B float 2. Yes, there is a B float 2, 3, 4. So yeah, and the third step is GPU is very memory hungry, and being able to show that you can preload the data using the big reads and then reuse it allows one to like implement a much faster kernels. I will point you to the repository that implements all the 3 steps later, and the results I've collected. Again, it was a while back. So very naive implementation that artificial intelligence gave me resulted in 8 gigaflops. So we're not talking about teraflops at all, right? Using this float force immediately gives us 35, and using mod4 jumps it again to 147. And if you do a little bit of prefetch, you can again almost double your performance to 231. Oh, interesting. So there are no bfloat matrices types. I wonder if it's coming in the next release of the metal. So that's kind of the first case study. And that's some local links to like, well, how to get started with PyTorch, probably cross operation. Well, I think the first one was a bitwise ops, but they're not interested in cross kernel was the first metal kernel added to PyTorch. For an example, for a good GMV kernel implementation, please look at MLX. The examples with one of the kernels that I mentioned here are in like my little repository, so feel free to check it out. Shading language specification, that's a very, very big issue that people request that was created in 2022. I think it's probably right now most commented issue on the PyTorch about what people want. Though we probably want to transform it because people keep requesting operations that was implemented a while back, but they are on a really old version of Python. And I guess last but not least, metal puzzles. So to get your hands dirty, because I think metal puzzles, they like MLX have a much more lightweight API to allow you to write kernels as part of your Python notebooks, which is pretty nice. So PyTorch have a very similar idea that I can show in a bit. That's all with the slides. I'm ready to move to a more interactive session and try to maybe implement a special I0 operator, but we can also like answer some questions.
Quick question.
Yeah. Oh,
If I
okay,
write
go
a
ahead,
program in Metal, is it always guaranteed to run on NPU and GPU and never on CPU, or can it also work on CPU too?
So Metal, that's a good question. So OpenCL originally can run on CPU and like other accelerators. I'm not sure if you can create a Metal CPU device. So like if you look at this, let me go somewhere here. Like metal benchmarks, right? If you look at the very simple, so I wrote a very simple kernel, and to get the devices, there is something called metal copy all devices, and I think this one just gives you one device by default on Apple Silicon, which will be your GPU. So no, I don't think it will dispatch to CPU.
So I may not be able to do either the CPU or a GPU. I mean, there is no way there would be a simultaneous execution of CPU and GPU then. Like for instance, I want to do a offload job to a CPU work, like zero offload or any of those, then probably will not actually work.
So you can do it right now, right? With PyTorch, like if you think about something like that,
Yeah, of course, you can do it over the PyTorch.
Yeah. But there's no clear way to do it in Metal, right? If you want to run something on CPU, you can, like again, you have multi-threading, you can create a thread and run something on CPU while you dispatch your work. So like, I didn't talk a lot about the main loop, right? But the main loop is you have a command queue, which is your CUDA stream, right? You dispatch a job to this command queue, says end encoding. So when you do commit, it actually sends us to the GPU. And then you can wait until like completed, do some computations and wait until completed. And then like you kind of parallelize CPU and GPU implementation to an extent, right? Like not a very clear like programming model, but it works.
Okay, thanks.
And Andrew mentions that MLX have a nice API for launch a GPU capture tool. So yes, there is something like that. I think it's called verbose mode. In PyTorch, I did something similar, so I hide it behind the flag. But if you use, if you look at this one, so I've like extended MPS profiler to have capture enable and start capture end capture. That allows one to capture the shaders that you're running. So I don't know why I'm hiding it behind the compilation flag. Maybe we can just enable it by default, but I'm unsure about the performance overhead. And with that, if you enable this MPS capture enabled environment variable, it will dump the things and print them into the like in the GPU trace, which I guess similar to the Metal debugger. Yes, so it will do the same thing. Oh, I see. They just explicitly expose start capture and capture. That's a good idea. If anyone wants to propose a PR that explicitly that exposes this functionality, like binds it to the Python, that'll be a good thing to do. So let me bring you. Sorry, I didn't open it in the right browser. That right. So this is the link that Andrew sent. How you can do this. Right, and this is like a similar idea how you can do it in PyTorch. Right, but there is no currently public bindings, and it would be nice to like expose them to Python. So feel free to authorize a PR if anyone wants to do that. And then the traces looks. Do I have a trace here somewhere? Okay, I have some trace, so I can probably open it, and that's a simple trio operation. So I guess we don't see a lot of interesting results. Because also, interesting thing about all those tools is that they're really bad when you do the video streaming. Because you're using the same GPU, I might not be able to show you anything of how to debug it interactively because I'm also streaming. So I run into it in the past, and I have to warn you that it might be the same thing again. Let's try. Oh no, at least I can debug. Right. So at least you can use like a tensor debugger and select any kernel, and then like at every step, it just records the value of all the variables, which is nice. Like there are all function calls on whatever. Any other questions? Okay, then let's, if people are interested, let's try to code I0 special. Maybe another interesting aspect, speaking of data types. So the big difference between CUDA and Metal is Metal doesn't have support for double precision floating point data type. It's only have a float precision, half precision, and B float. And surprisingly, to the best of my knowledge, again, like M2 does not have a hardware support for bfloat 16, but somehow it is faster than using float 16. So even though it's simulated, again, if you think about it, like you can convert from float 16 to bfloat 16 by just shifting to the left and right. And I guess that's what happens under the hood, and the operations is just like performed over float 32. But still, somehow those computations are faster if you use bfloat 16 in the simulated mode than if you use float 16. Cool. Let's try to code this one. So I just tried to enable some testing, and I noticed that there is no such thing on MPS, right? And we can probably just quickly check that it is indeed the case. So if I do Python, import torch, this one works, but if I say device equals MPS, it will fail. Right. So very first thing to do is you need to implement an ATON operator for MPS, and you can do it by unless people have questions now.
No, this is super interesting. You know, just like if you want for questions, like we can interrupt you. So just keep going.
Sounds good. Okay, so first thing I'm going to do is I'm going to add like a native function. Right. So let's search for I0, pointwise. So we have CPU CUDA, but no MPS. So let's add an MPS here. And try to compile it. Now, just for clarification, I already have like a PyTorch pre-installed, and I installed PyTorch in something called develop mode. So essentially what it means is if I'm anywhere and I do import torch, then torch file points to like my GitHub repository. So it makes it very convenient to interactively debug and develop. So I added another ATON operator. It runs a little bit of a code gen, and it compiles a few things, and it will fail to link right now because now it says you need to call certain MPS operator, and I didn't implement anything. So I suspect when we compile this one, it should crash. Oh, well, it should fail to compile. Sorry, it will compile, but it will not link.
Yeah, I think you're the first speaker who's attempted to like build a library from source on live. It's very brave.
If there will be a blue screen of death, I'm not maintaining macOS, so I will not be responsible. But I'm not sure why it's taking a while. Let's bring some things here just for something like that. It's still compiling. I'm surprised. Usually it's much faster. And my yeah, go ahead.
So Simon's asking, is there somewhere documented how to make PyTorch link to your Git repo?
Yes, if you go to PyTorch developer, like I think it's in contributing MD.
Contributing, yeah.
It's, yes, so tips and debugging. Right, so you do this, set up, develop, and then you can do this. But actually, since then, I wrote a really nice tool. So I very often have to debug something. I can probably like show you how it's going on once it finishes. I don't know what it does. There's something weird going on. I haven't updated my macOS recently, so I should be fine. So I wrote this tool called build with debug information, which allows one to rebuild just one file. We'll probably use this tool later on, and it creates the same links for you. So I can post this link here, but I probably need to update it there. So you don't need to do it anymore because there is a dedicated tool that can do it for you unless you are doing it on Windows. Sorry, Windows is hard to support. So, oh, sorry, not this one. I don't know why copy and paste didn't work. Oh, interesting. It just failed to launch. It doesn't. Very interesting. Is that? What is our example? Okay. So dispatch is missing for kernel MPS. Nice. So that's a good sign. We changed the error message from not implemented to dispatch is missing. Now let's implement a dispatch. But first let's find where it's implemented in the associate and native CPU special ops. No, let's see on CUDA. CUDA unary special ops. Here we go. And let's create something similar, native MPS. Oh, sorry, I don't like, people usually do Visual Studio. I don't know how to use Visual Studio, but I use Vim. Let's create special ops here. And we do want to do I0, right? So we register dispatch here. Takes tensor iterator. I don't like tensor iterator. Well, I like tensor iterators and dislike them, but let's try it. So I think this will just print as zeros unless I forgot to include something. No, thank you. I used to use Emacs. Okay. My 0 MPS, it must be static. Sure, why not? Now, if we run the same thing, it will just give us zeros, but it gives us as many zeros as we want, which is really great progress. So I0, and all it does is call something called calc I0, which is a very simple function. I think it should be implemented somewhere here. Native CUDA. And yes, calculation of I0 is very simple. Again, it's I don't know why we do a scalars then, but so let's create I0.metal and try to copy and paste this thing. So I don't need static, I don't need inline, and unfortunately no host device. So I think the big difference between like Metal and CUDA is that Metal is purely GPU, there are no host device functions.
So Nikita, like, is this like, did you sort of imply here that when in PyTorch and Python land, when we're calling to MPS, it's kind of like a fake operation in some sense? Like you're not actually ever sending to the device, it's always running on the device. Is that accurate?
No, well, so 2MPS still does something to the tensor. It converts it like, well, to CUDA doesn't actually, well, it does send it to CUDA. We still use the separate memory right now for MPS and CUDA and CPU, but you can read technically. So all of our MPS tensors are mapped to CPU. You can read them. The problem is when CPU tries to write them. So like in Python, we don't have a really good API for invalidating caches or having something like copy on write, because if you just map the tensor to CPU, it will not be visible from the start. Anyway, does it make sense?
It does, yeah, thank you.
So like, I don't know, if I'm to demonstrate storage MPS storage pointer. Do you have storage? Yes. There's a pointer or something. Data? Sorry, I'm a bit confused. Let me. Like something. Sorry, I always forget all this. Type storage, and we can create a tensor self-storage. Storage bytes. Let me quickly Google. No, I don't use Copilot. I just use a very old plugin called uCompleteMe, which is just a LLVM front end. It does have Copilot, so surprisingly, so I was almost there. It's data pointer. No, it's not data pointer. It's just X have a data pointer. Yes, X have a data pointer and Y have a data pointer. So you can see there are two different data pointers. Unfortunately, there are two different storage types. But like you can create a bytes object from this data pointer, and actually you can read an MPS memory, but like if I'm going to modify it, it will not be reflected. So it's better to copy it. Anyway, where was I? Here. So I have calc I10. I need Chebyshev coefficients. Oh, I need both of them, I guess. No, only A. Oh, no, it's in B. unsurprisingly. Thompson tells me that's probably all I need to be able to compile this thing. So let's try to compile and see how bad I am. And I also probably need I keep forgetting. Yes, I need to include metal standard library. Wait, then line std tuple. I'm not sure if I have tuple in the. But let's see what will happen. So the metal compiler is unsurprisingly called metal, but unlike host compiler, Visual Studio Xcode does not expose it as a regular command line, but you need to prefix it with something called xcrun, which stands for Xcode run. Metal 0.metal. Yeah, so there is no std. And I don't know if metal indeed supports tuples. Can I pound include tuple? No metal, let's give it a try. Yeah, no tuple. We can implement tuples. Should I implement tuple or do something simpler? Let's implement a very simple tuple. Who stops us? Right. Okay, and pointers, yes, that's an interesting thing about metal. Unlike CUDA, you need to have variables and function scope cannot be declared static. Yes, welcome to metal. So let's make it a little bit more ugly. Let's just say that they are float arguments because we can have them as doubles and we'll be downcasting them. Oh, const versus constant.
I mean, I actually hear like which C++ version should people be using if they're using metal? Like
It's something like C++14, but again, like it have all the C++14 language primitives, but it doesn't have the C++14 standard library,
I see.
right? By std tuple, you can't include it, right? So you have metal stdlib. So I don't know if that answer makes much sense.
It does. It's an interesting choice though. Like why do this if you're Apple versus just implementing the standard?
Because why do you want to implement a standard library when you don't have to?
Fair enough.
Let's see. Bye. And we need this function. That's the only implementation. No, there's a GTrator implementation. We probably should have followed this one. We just copy and paste this one. It's much faster. And it will probably work as is without any optimizations. Okay, this one compiles. We just now need to write the kernel, which takes input and output and calls this function. And I assume that I0 is always one-dimensional kernels, right? Input outputs for each element of the input. Oh, I see. So interesting. Well, I think during this recording, we will implement it for one-dimensional tensors, and then I'll later extend it to the multidimensional tensors. So let me write the kernel. Let's write a floating kernel. I'm kind of lazy. I will write constant input output and I need input output and I need linear index. That's it, right? Let's again, this is even simpler. So like unfortunately, PyTorch is a little bit convoluted. It needs a lot of assumptions. So if we do something like that, we still can compile, right? And output of index equals I0 of input. Yeah, it works. So we have a kernel. We just need to connect it back to our buffer here. So I need now, I guess, for comparison, yes, operations. What would be the simple triangular ops is pretty simple. So we take shaders here. Mhm. Well, PyTorch have a lot of weird operations. I forget why we need these Bessel functions. I think one of the normalization schemas requires one, but it's not the most popular op, right? But it's a very simple to implement. So anyway, right, we just take the implementation from here and post it here. And now we want to call the kernel on the iterator. So I0 kernel. This is from slide 2. All right. Oh, it's just called A0 and then word float. I need to. So we here we finally will compile it at the runtime. We can get the current stream. And let's just pull it.
Nikita, do you mind taking a few questions, or do you want to just
Sure,
finish?
yeah.
So I have three at least. So first off, when I see this dispatch sync with rethrow, like what is this really doing? It's
Oh,
basically
okay,
it's
good point. I forgot to mention about it. So, like macOS have an interesting threading paradigm called dispatch, Grand Central Dispatch. So instead of creating a classical threads, you can create so-called dispatch queue, and then the queues can be parallel and synchronous. And when you say dispatch sync with retro, it says that the block within, like from here to here, right? So similar to C++ Lambda. So C++ Lambda appeared, if I'm not mistaken, in like C++ 11, but like Objective-C has a paradigm of blocks for a while back. It's very similar to Lambda. It's a capture everything, right? And here is your Lambda, and this function dispatch sync. So with retro is our implementation that throws C++ exception, captures and rethrows C++ exception to the original one. But this might execute it in the context of a different thread or whatever. But what this guarantees that like only one block can run, because we like you see here, I create something called command encoder, right? And I make these commands, and those commands must be executed sequentially, right? Because GPU does not know what happens in between. So what I'm saying here is that I want to guarantee that those 1, 2, 3, 4, 5 commands will be executed sequentially. No one else can execute any commands to the GPU at this time. Dispatch any commands to the GPU. So GPU can be running something, right? In the background, there could be other GPU threads. But I'm saying that within this stream, this is the commands I'm executing. With the CUDA, you need to do something similar, right? There is a CUDA guards. But in like on macOS or if it's Metal, you can just guarantee like that. Like essentially, a programming API requires you that only one thread at a time can dispatch
yeah.
commands to one stream, and dispatch sync just guarantees that. If you like, this is a standard part of the macOS operating system, schedules block for execution. Most of the time, if your code is sequential, it's no operation. Right, it doesn't do anything. So if you only have one thread, you can like in all of my examples, and like if anyone checked out my
I see. Yeah. So like if you were just like a Metal author, you might not have to worry about this, but because you're merging your code within the PyTorch library, it
correct,
might be
yes, because we're
scheduling
using
other
PyTorch, yes,
kernels.
yes. So like
And
most
so
of
you
the
have to be
time, this
safe.
would not do anything. But if you're doing something weird, or especially like if it's a like backward propagation or something that happens asynchronously, you need to synchronize. But it's not, it doesn't really happen. Another thing,
Got it.
auto-release tool, it's another language of Objective-C. So Objective-C is a very strange language that have a lot of interesting syntax. Apocryphal theory is that when Apple first needed to implement something like Objective-C, they didn't have a compiler engineers, and the first implementation of Objective-C was just a preprocessor, and so they wanted a construct that would never be encountered in normal C code. So they do this at auto release, or this very weird like brackets as a first operation of the string, which means like invoke object. Invoke method of the Objective-C class.
And so speaking of Objective-C, there's no limitation on us. Like this could have been like Swift code if you wanted it to, right?
Yes,
We're
yes,
not.
you can write Swift, you can write
Okay.
Objective-C. It's just like, yeah, in PyTorch, we just choose to do the Objective-C because Swift runtime is a little bit more involved. So like the great thing about Objective-C, it have a zero runtime overhead. Zero like runtimes that you need to link into your application. It's all part of the operating system. With
I see.
Swift, because Swift language evolves a little bit faster, whenever you compile, you need to bundle parts of the Swift runtime into your application. This is why we decided not to use it. But at some point, if people feel strong, they can rewrite it to Swift.
Okay, got it. Thank you.
And, yeah, I need input and output tensors. I'm trying to recall how to do it. I guess like input tensor, I can do auto input. Input. out size. No, tensor iterator base is not defined. Sorry. Now it will be a bit better. Okay. And so now let's see how bad I am at writing code. Pretty bad. What did I do wrong? This change has dependency on native function.yaml. Consider your change should be better placed in another file or more specific. Cool. Will it just work? I'd be very surprised if I didn't make any boo-boos anywhere, but let's see. Well, it prints once. I don't think that's what we expect to see here. But it means that it's likely working. Maybe I confused inputs and outputs. And now let's use this validation. Or we can maybe capture them. So let's see if we do any out of bounds writes. By any chance? No, it just once. So what am I doing wrong? X is less than 8. Exponent of Chebyshev y 30. Otherwise, we do this and exponent of Chebyshev b25. Everything is correct. And input is first, output is second. Output of index equals input of index.
When you say MTL set buffer, like what is 0 and 1 referring to?
It's an indexes in the function. So you can be really verbose and write something like that. I think if we look into any other, like you can specify which indexes, but essentially like this is argument, this is like a first argument, second argument.
Got it,
Right,
got it.
so let me try to find something with tensor iterator base in like MPS code. Maybe I. Oh, copy sign, for example. So you see, usually we specify just buffers like that. All right, so let's see how we implement copy sign. Binary MPS implementation. So input 0, input 1, and just output. Oh, they both outputs. That explains what I did wrong. Now let's see. And we get the expected results, so it just works. Is that the expected results? Let's compare it to the CPU. And that
Yep.
seems to be the case. So you see, we wrote I0. I think it will fail as soon as you try to pass a non-contiguous tensor. And this is something that I need to fix. But let's try to run the test that should expose the problem. Or I don't know, I can create a PR and post it for the people to observe, and then we can continue iterate on the PR. That will work as well. Let's probably do that. Because I think the questions people very often ask is how to test it. So luckily in PyTorch, we have something called operator information. And what we usually do when we implement operators for accelerator, we compare them against CPU implementation. Right, so if I do something like test MPS, and I'll try to run a zero test, it will, well, it even crashes everything. So it means that I'm doing something really, really bad. And let's try to figure out what we're doing bad. No. The default MPS generator. Oh, because we indeed corrupted memory. I suspect we did. Let's try it again. No. Okay, I'm a little bit confused. Let's modify our implementation to just throw an error without trying to do anything, just return, right? Because if we just return, we can't corrupt the memory. And it should just work. No. Oh, yes, I didn't rebuild my Python binary. Yes, sorry. That explains what's going on. While we're waiting for that, any other questions about what's going on? And I think, did I create a PR?
I think, yeah, maybe Nikita, maybe now's a good time for because like one thing I noticed is that as you're going through this, you're like copy pasting a lot of your own code. You had a lot of like tools that you're using that you found helpful. And I think like basically the main theme people are curious about is like, great, like how do I just do what you did now for like another op? So maybe it'd be helpful to sort of like show people what are the options available to them.
Sure. So indeed, like the workflow, as I think I mentioned on like this slide, workflow should be something like that. You implement your kernel, you compile your kernel, making sure it works. You wrap it with metal shader library, right? So if we go back to while it compiles, right? So metal shader library is a class that just compiles the metal shader and makes it available to your application, right? And then you can do leap get function, right? Get pipeline name for function, and it creates a pipeline object that essentially binds a function to the kernel, and then you can invoke it. So like you said, the buffer and whatever, the thing that you need to remember is indeed how to, like what is tensor iterator? So I think to write PyTorch pattern operators, you need to know certain things, which I think you also need to know when you write a CUDA tensors, if tensor iterator for some reason doesn't work for you. So, but this is essentially like a core of operator implementation. I plan to add something that will make it a little bit more similar to, but it's not done yet. So if anyone wants to help me with this refactor, but I plan to add something similar to what MLX is doing, when you can just implement a shader and provides a function signature, and we write this boilerplate code for you, because all of that is a boilerplate, right? There is no real logic. Well, the logic starts a little bit here. So all, like when you're talking about binary operators or unary operators, sorry, just for any element-wise operators, you can always treat them as a one-dimensional job, right? So you have some operations that you perform with element X or elements X and Y, and you save them to element Z, right? And you can always treat them as a one-dimensional job. There is nothing you need to know about the tensors geometry. But when you try to do something more involved, like matrix multiplication, you want to dispatch a two-dimensional, three-dimensional jobs, when you can organize your threads in a nice thread groups and they can use shared memory. Right, so this is something we didn't touch because it's a beginner, like metal, it's not an advanced one. We didn't touch and talked about anything related to like organizing thread in different directions. But if you want to implement like unary kernels, then one-dimensional job is what you want to do. I guess like I could probably answer better if you prod me with some, like, or anyone prod me with the most specific questions, what you want to know about a specific part of this code.
Yes, so I like my sense is pointwise ops are like a better like starter task. So maybe the tracker that like Albin had up has like enough like good pointwise ops, and maybe people should just start with those.
Indeed, indeed it does. Yeah, and like for all the pointwise ops, again, I'm apologist for a lot of boilerplate code, but this is nothing but it. Like I think the parts that we haven't touched yet, so when it finishes compilation, and it does, so now let's see that I0 should just fail, because everything works. Yes, expected failures. And if we uncomment this one, so the things that is currently missing, so you see this one scalar to metal type. So right now I implemented it only for float, but I probably want to implement it very similar for half and B float. And I can just copy and paste, or I can use templates to do that. This operator is so trivial that like copy and paste in templates sounds a reasonable thing to do, but sometimes you want to do something like that. And you see it in lots of other kernels, right, is people do something like that. And then you give template kernel, the host name, like I0 floats, and then you like explicitly specialize it, and we very often do it through like through this type of template, through this type of like preprocessor macro. Let's see if this works. So this is identical to what I've written before. But maybe I made that typo here and then it will not work anymore. Oh, thank you. Yes, indeed. There are lots of tutorials of how to do that. So if you want to just be a bit more familiar with the basic implementation, you're more than welcome to try following those. And I made a mistake again somewhere. Oh, because I'm still returning. Oh, no, I didn't make any mistakes. Interesting. So let's see what will happen. So if instead of float 32, if I'll try float 16, we should see an exception saying that I0 float 16 could not be found, right? Cannot create a function state object for I0 half, right? And so what I want to write here is, right, now it will work for half precedent types. But I don't know, Mike, I can continue implementing this, or do people have some other questions? Because I think it might be a bit boring and I might need to answer some like practical questions.
Yeah, I think probably now is like a good time to start wrapping up. So yeah, like I guess if folks have any questions to Malfit, Nikita, he goes by Malfit on the server as well. And otherwise, yeah, let's just take the last couple of questions. I see Simon's asking, can you also just show the tool you talked about earlier?
Sure. Although let's do that. That's indeed an interesting one. So like, let's look at this again. You can use Visual Studio if you want to debug anything, but I'm a bit lazy, right? So like, let's do this, right? And we know that we implemented it for float 16. Let's add bfloat 16, right? Because we haven't. And if we run it, it will throw an exception. And if I say that I want to stop on a C++ exceptions, it stops on C++ exception, but my backtrace is not very informative, right? Like, I don't know what I'm doing, right? I don't see anything. And I want to see the line information. So what I can do, I can use this tool called build with debug info and say, I don't want to like boil the ocean. I don't want to rebuild. So like, why not build PyTorch with debug information by default? First of all, every time you link, it will take like 5 minutes because your PyTorch binary will be huge. And if you build everything with debug, your binaries will also be very large and very slow. And like, it will affect how you can run some things. But if you know that you want to debug like a specific thing, and you know that this, I don't know, function is implemented in, because we just added it, right? So we know that it is in spectral ops. So I do this, right? I call Python tools build with debug information and just say this one file, please. And it reveals just one file with debug information. And now if I repeat the same exercise, right, and want to see the breakpoint, I can see the nice line information. I can see all the variables or whatever I want. So 6-8 row, I cannot. But here is my line information. here, and I'm going back here, and I can see everything, right? Here's my iterator, here's my input tensor, here's my output tensor. Like this is my stream, right? And I think I keep forgetting, this is a GUI, right? So if you don't know, LLDB have a nice debugger that you can use. But again, like you see, so let's go down, like suppose for whatever reason we want to go down and we see, well, you know what, this one is not, so we have debug information here, but we don't have it here, right? Which is like, where is this get pipeline state implemented, right? You can do it with grep, but I know ahead of time that it is implemented here. So I say 8 native MPS operation utilities. Now I compile 2 files with debug information. And I will see more line information as I go through the code. And again, it allows me to set breakpoints by line numbers and all that stuff without like recompiling. And it should work for your CUDA as well. I don't remember. Yeah, you see, so now I recompiled operation utils with debug information, and I know exactly where I am. And again, I can like, yeah, well, here's my code. This is what I did so far. So it will work for CUDA as well. I don't remember if I add dash capital G. So maybe the thing that I didn't kind of mention that in PyTorch right now we rely on so-called JIT compilation. So we JIT compile all the tensors, all the metal traders. This will change in the future. But in CUDA, we usually pre-compile it. And when you compile CUDA shader, you have like 2 options. You can compile CPU code with debug information, but you also can compile GPU code with debug information. Then you need to use CUDA GDB or something. And in that case, you need a dash capital G. So dash lowercase g when you do NVCC dash G will insert debug information for your host code. Dash capital G will insert debug information for your device code.
All right. Well, thank you, Nikita. I think now might be a good time to like end. Thank you so much for coming on. I think, yeah, like I said, everyone, like and Nikita goes by Malfit on the server and on GitHub as well. So if you're like looking to get your first like metal kernel merged in, you know who to tag. Thank you so much, Nikita. So next week we're gonna have like Daniel Hahn, who's gonna be talking about like Onslaught. So yeah, look forward to see everyone next week. Thank you.